Now we have a presentation on maturity and functionality of electrified boosting by Peter Davies, Senior Director, Powertrain, Garrett Motion Inc. Welcome, Mr. Davies.
Good afternoon, ladies and gentlemen, and thank you for inviting me to your conference. My topic today is maturity and functionality of electric boosting in off-highway equipment, and in your particular case, the possibility in tractor machinery. You know Garrett, of course, because of our activities in turbocharging. We're the world's largest turbocharger manufacturer. But increasingly, as the world electrifies, we'll be branching out into electrified boosting and then into other technologies that go into hybridized vehicles and even full electric vehicles. You'll also start to know us for our activities in the connected space and in cybersecurity. So what I'll talk to you about today is the breadth of our product range. We work on projects from passenger car through to off-highway machinery, which you're interested in. But one thing these have in common is that all of them are hybridizing in order to reduce CO2, in order to reduce harmful emissions. Systems are coming on board of the vehicles to do onboard diagnostics, onboard management, and energy management. And these are the domains that Garrett will increasingly be involved in. So with this as a backdrop, it's a big opportunity for hybridized boosting, and that's the topic of the discussion today. Garrett, it won't surprise you to know, is involved already in many forms of hybrid boosting. We have, since 2016, in series production, a hydrogen fuel cell compressor on the Honda Clarity vehicle. Now, this is a powerful machine, and branching out from this, we've now developed a range of electric compressors for internal combustion engines and electric turbochargers for internal combustion engines. So in the press in the next few days, few weeks, you will hear about the series launch of the world's first electric turbocharger, or at least the first high volume electric turbocharger. Of course, this is in racing today. For those of you who have watched a Formula One race, the series is once again hybridized. And in our case, we support the Formula One teams, actually Ferrari, in their efforts to win that championship. I will speak to you about both of these technologies today. And I'll try and bring it to the relevance of how it may help you in farming machinery. So let's talk about the electric boosting opportunities that we have in internal combustion engines. We have essentially two systems that we can deploy. One is a turbocharger combined with an electric compressor, and you can see that they're piped together on the engine system like this. The second, we can take the electric element of the compressor and we can integrate it into the electric turbo. And then we go back to a similar arrangement to a standard turbocharger on an engine, but here we're just connected with the electrical network onto the turbocharger as well. What do these systems bring in functionality? Well, they bring a lot, some of which is common between the two of them, but all of which is additional to a regular turbocharger. First of all, we're able to think about downsizing. In a 6-cylinder world, we can think about downsizing to 4 cylinders. In a 4-cylinder world, we can think about doing the same duty with the engine with just 3 cylinders. And this is something that you may be interested in. Through downsizing the engine, we have an immediate improvement in fuel economy. We run the engine at more optimum loads and higher brake thermal efficiency. We have systems which are much more spontaneous, much faster in response, and as such we can run EGR during transients, and we can reduce NOx significantly. In on-highway applications, we can also boost during the braking cycle. Perhaps not so relevant for a tractor, but what is relevant for a tractor is we can go into the world of energy management and thermal management. One of the other features we have is part load supercharging, and the unique feature of the e-turbocharger is that we're able to do turbo compounding or recuperation or regeneration. People use different words for it, but it brings additional fuel savings when we run the turbocharger in generator mode. This is something that only the e-turbo can do, and it's the thing that differentiates e-turbo from e-compressor. Otherwise, they're very similar. Let's talk about the energy flows in the system. Here I've simplified the diagram. We have the engine, we have the turbine, we have the compressor. Generally, the energy flows in a clockwise direction, and we push air from, or we draw air from the atmosphere and we push it into the engine. We fuel the engine, we extract waste heat from the exhaust, and that drives the compressor. And that is a cycle which in steady state reaches an equilibrium. The turbine work essentially equals the compressor demand. And then we pass the exhaust to the after treatment system and to the outside world. So of course that we have to have good aerodynamics, we have to have low friction, we have to have good efficiency. But how does it actually work in a transient? Well, the first thing that you do when you ask the engine to go on load is you give it some fuel. The second thing that happens is the turbine starts to see the increase in enthalpy in the exhaust, and it can actually start to expand the exhaust and produce some useful work. Only then can it accelerate the compressor, and only then can the compressor give the engine the air, or more specifically the oxygen that it's looking for to burn the fuel. So the issue with this system is that it's fundamentally a lagging system. And it means that we, in tractors, we use 6-cylinder engines instead of 4. We use 4-cylinder engines instead of 3, just so that we can get the load acceptance and the pickup that we need when you start working with these machines. If we now consider the e-turbo case, and we insert an electric motor onto the shaft of the turbocharger, the whole dynamic of the system changes quite significantly. The electrical energy from the vehicle electrical network can be used directly to energize the turbocharger motor. That motor only has to overcome the inertia of the rotating group, and it starts to accelerate very quickly and start producing useful work. At that point, the engine can also inject fuel and react, and it has the oxygen it requires to perform its combustion immediately. What happens next is interesting, because the turbine obviously starts to generate useful work. It starts to do its expansion and recover waste heat. And what happens is we reach an equilibrium when we're able to turn off the motor. And we're back to the original quasi-steady state cycle that we were talking about a few minutes ago. But what happens if we continue? What happens if there's more exhaust enthalpy than we actually need to drive the compressor? What happens if the engine were fueled just a little bit more? Well, what would happen is that the motor would become a generator. We don't want the turbocharger to rotate any faster. We don't need any more air in the engine. So we actually start to break the turbine with the electrical machine. Of course, the electricity has to go somewhere. So where do we put it? Well, we put it back into the hybridized powertrain. In this case, I've shown an ISG just schematically connected to the engine. It could be a belt starter generator as well, or it could be another part of the vehicle electrical network. Of course, we have a battery there, which maintains the voltages and everything else on the network. And what's really interesting at this point is the next step is we start to think about the motor on the e-turbo as not just a motor and not just a generator, but one which is constantly changing between motor and generator. And at this point, we get into the concept of bidirectional energy management and the concept of managing this in the time domain so that there are times where it's a good idea to use it as a motor, times where it's a generator, and we start to manage the state of charge within the whole vehicle electrical network. So these are the functionalities that electric boosting can bring. I use the turbo example because it's the one that goes the furthest to this concept of energy management. The electric compressor can do that also. Going on to the next step is we start to think about how much energy can we save. Well, in one of the earlier slides, we said 3% in fuel economy. And this is on top of any downsizing effect. In this schematic, we have exhaust enthalpy being converted via the motor through the power electronic and back to the electrical machine on the crankshaft. This allows you to defuel the engine. Yeah, if you put in 10 or 15 kilowatts through this route from energy that's been recovered in the exhaust, then that's 10 or 15 kilowatts that you do not need to produce with the engine itself. So you're actually defueling the engine in order to produce this power. You can think of it as an EGR device. Many of the turbochargers we supply in the world are variable geometry. What happens in exactly the same setup, but on an EGR engine, is we're able to start thinking about the variable geometry turbine controlling the P3, the pre-turbine pressure, and essentially driving the EGR loop. So this drives the pressure differential that pushes EGR back into the cylinders, and that becomes your EGR control parameter. Of course, that takes away enthalpy from that takes away power from the turbine shaft. We don't mind because we can add power on the motor now. So we go to the situation where the VNT is controlling the EGR and the MGU or the motor on the shaft is controlling the boost pressure. So we can boost as much as we like with the motor, and it doesn't matter that maybe we don't have enough enthalpy on the turbine. Another function we can put it to is after treatment thermal management. This is reasonably complex, but there's several features in this type of arrangement. First of all, we have a bypass around the turbine. We can position the bypass to set the P3 here, and we can play unexpanded exhaust directly onto the after treatment system with the proper geometry and design. Of course, this takes away flow from the turbine. It takes away power that we could extract from the exhaust, But again, that doesn't matter. If we have the MGUK and the MGUH, we can take power from the engine crankshaft. We can convert it electrically to power on the turbocharger shaft, and we can boost. Positioning the valve correctly, sizing the turbine correctly allows us to control the flow of EGR. So in the warm-up stage of the engine, we can recirculate EGR. We can play unexpanded gas directly onto the aftertreatment system, and we're putting the engine under higher load because we're actually boosting from the engine. We're supercharging. So the combined effect of that is the engine comes onto high load, we recirculate hot gas, and we play hot gas onto the aftertreatment system, and you get to catalyst light off much faster than you would do otherwise. So if we do some calculations when we look at the flows and the pressures that we require, 10 kilowatts takes us very easily to 1.4 pressure ratio and maybe 180 grams per second of airflow. And you can pick off the points on this kind of chart as to where you want to run in your warm-up cycle. But this is a very effective method of thermal management. So I'm coming to the end of my presentation now, and I wanted to come perhaps more to the point on tractors and off-road machinery as to typically what you can expect to do with an electric boosting system. Now, a six-cylinder base engine has a time to torque normalized here to 100, and typically we're talking about 5 to 6 seconds to reach full torque in certain load steps. It's not obvious, but an electrically boosted four-cylinder is much faster than a six-cylinder base engine. This data is normalized, but it's based on test results that we've made. And what we can see is a 75% reduction in time to torque. And if we configure the systems correctly, we can give up to 20% more engine power as well. The advantages a four-cylinder has over a six-cylinder is, of course, it's lower friction, it's lower cost, and because you're operating it closer to its peak efficiency, it's lower fuel consumption. So in the world of off-highway, I think there's a lot of value created by the fact that you can once again consider downsizing because you've got benefits in fuel economy, you've got benefits in packaging, which are very important, and you've got benefits in system cost. With that, I'd like to summarize my presentation. Electric boosting offers many benefits. Contrary to popular belief, this is not only Formula One technology. This is not something for the future. This will debut in passenger cars in my part of the world in 2021. We are literally days away from launching series production of electric turbochargers. Electric compressors will follow in 2024, and we'll be applying them through demonstration projects in the coming months to both on and off highway applications. Specifically for India, we think of the 75 to the 100 kilowatt range of machinery that you use in agriculture. And as a problem statement, one that looks very attractive to me is considering you use a lot of 2.x three-cylinder engines today, but they're limited in power density. So you use a 3-liter instead. I wonder what a electric boosting system could mean for you if you, in the future, if you consider downsizing this 3-liter to a 2.x with 1 cylinder less, much less friction, higher loads, better thermal efficiency, and a system that can help you meet the emissions challenges of the future. And with that, I'd like to close my presentation, and I'm more than happy to take questions about the technology or anything else you might raise about Garrett. So thank you very much.
Thank you, Mr. Davies, for an excellent presentation. Time for the next session. Stay tuned.